Highly configurable software underpins much of our computing infrastructure. The Linux kernel, for example, is used in billions of computing devices, and it has over 15,000 configuration options controlling drivers, memory management, architecture. And this constrained configurability makes its widespread use possible, but it also opens the door to invalid configurations that produce broken variations of the software. Developers provide configuration specifications to help mitigate this problem so that users can avoid invalid configurations. And for small programs, these specifications might just be a text file with some informal instructions about how to configure the software. But large, widely used projects often use machine-readable specification languages that can be automatically enforced. The Linux developers, for instance, created the Kconfig language for declaring configuration options in their dependencies. But these large configuration specifications make maintenance harder. Even though they're meant to ensure software correctness, that the configuration is creating a correct piece of software, with Kconfig having 140,000 lines in the current Linux Kconfig specification, this specification itself becomes a software product that has its own maintenance challenges. And the Kconfig language has complicated and subtle semantics that go beyond just feature modeling. For instance, it has a type system. It has so-called invisible options, which are meant for automatic selection of options under certain conditions. It has constructs for defining the user interface. Here's an example of Kconfig drawn from the Linux kernel source code. The config keyword declares the option. Tri-state is its type. It's effectively Boolean with an extra state for some special build features in Linux. The prompt determines the visibility to the user of this option. Depends on are the direct requirements that this option needs in order to be enabled. And select force enables another option. So if touchscreen ADC gets enabled by the user or another select construct, then IIO buffer CB gets force enabled. And these three constructs, along with a few others described in the paper and in the Kconfig manual, conspire to create the behavior of constraints specification in Kconfig. Now, the Kconfig manual warns about the intricacies and the subtleties of the Kconfig semantics. In particular, there's the unmet dependency bug that it highlights. And quote, it says, select should be used with care. Select will force a symbol to a value without visiting its dependencies. And what this means is that if not used carefully, select can actually subvert the dependencies that another option has. And this can result in a broken build because of this subverted dependencies. And even if the Kconfig tool validates a user's configuration as valid, this bug can still cause a broken build. Here's an example of an unmet dependency that we found with our tooling in the wild. There are three options here: touchscreen ADC, IIO buffer, and IIO buffer CB. And the unmet dependency happens when the select construct force enables another option, subverting the dependencies of that option. And it happens because here, IIO buffer CB depends on two other options, IIO and IIO buffer. But touchscreen can force enable IIO buffer CB. So if this reverse dependency caused by the select forces IIO buffer CB to be enabled, but IIO buffer's direct dependencies aren't enabled, then we have the potential for a broken build. So the ultimate goal of our work is to automate the analysis of configuration specification languages. As software infrastructure grows in size and reuse becomes more prevalent, the management of these configuration specifications becomes intractable by hand. And we use this problem of Kconfig and the unmet dependency bug as an organizing challenge for developing our analyses. And it's a difficult problem because these specifications are so large, with about 140,000 lines of Kconfigs and thousands of these select constructs. And there's also just thousands of configuration options, meaning there's an enormous space of possible input configurations that makes brute force checking or analysis just infeasible. So our solution to analyzing specifications is to use static analysis. Because static analysis means that we can check all input configurations simultaneously, making it feasible to find many bugs or do lots of checking automatically for lots of input configurations. And our analysis approach is based on a software model checking technique. We automatically model the Kconfig specification as formal logic, and then use automated theorem proving to verify the existence or absence of a bug. The challenges to this approach is that, unlike with programming language model checking, infrastructure just doesn't really exist for analyzing Kconfig. So we had to develop this infrastructure largely from scratch. And also, model checking depends on having a formal specification of the semantics of the language that you'd like to check, and existing semantic descriptions of Kconfig have largely been either informal or just missing behaviors needed for finding, for instance, unmet dependency bugs. The contributions of this particular work are a new formal semantics for Kconfig, a verification-based unmet dependency bug finder with some optimizations to ensure scalability. We implement this semantics and the bug finding technique in a new infrastructure, and we evaluate our infrastructure and bug finder for performance, precision, and impact. We show through our empirical evaluation that our bug finder is both fast and precise, and it's resulted in bug reports and patches that Linux maintainers have mainlined into the Linux kernel source repository. Here's an overview of our infrastructure. Kextract simplifies the syntax. Kclause implements our semantics by translating syntax into logical formulas that represent the behavior of the program. Kismet generates verification conditions to prove whether there is an unmet dependency bug. And Klocalizer dispatches these conditions to an off-the-shelf automated theorem prover. If there's an alarm, it generates a test that we can use to actually validate whether the alarm is a true positive. We evaluated our bug finder on a recent version of the Linux kernel, and the one thing to point out here is that there's actually 28 Kconfig specifications in the Linux kernel, one for each architecture that it supports. But because of this hardware abstraction layer design, these Kconfig specifications actually share a large portion of their syntax. But we run Kismet on each of these 28. We first evaluate our tooling for precision, and we find 151 true positive bugs. There's 781 before we deduplicate across these shared Kconfig specifications. And we've actually validated that all of these alarms were true positives by generating tests and actually trying to build that kernel and finding that, yes, Kconfig detects this as an unmet dependency. But one thing to keep in mind is that we employ some underapproximation of non-Boolean options. Non-Boolean options represent about 5% of all configuration options, while tri-state and Boolean are about 95%. So we underapproximate non-Booleans just for scalability reasons. But this means we run the risk of having false negatives. Now, we don't have ground truth for how many bugs there are in the actual Kconfig specifications. So to get a proxy for this, we ran the random configuration testing tool that comes with Linux for over the equivalent of several months of sequential time. We have some parallel computing to do this in about 4 days. We generated about 11 million of these files and found 8 true positives that Kismet missed due to this underapproximation. Each Kconfig specification took between 37 and 90 minutes to run, which we believe is fast enough for the pace of Linux development, which produces a new Linux Next version each day. And this represented about 10 to 12,000 select constructs in an hour for each specification. We submitted some of our bugs by hand, and this was limited just because we have to do this by hand, and it takes some time to actually generate these reports, look for a patch to fix it, converse with developers. And all the reports so far were accepted as true. Some are still pending. One was accepted as true, but maintainers didn't want to fix it. And 15 of our patches have actually been mainlined into the Linux kernel source code.